some more basic derivatives. And so this is just power rule and exponential function. Okay. So at this point, we have one version of the power rule, right? We saw that at this point we know that if you take the derivative of x to the n, then you get nx to the n minus 1, right? Where n is some natural number, right? That's and we remember how this comes, right? We figured this out, or at least we thought we believe this is true because of Pascal's triangle, or your understanding of a plus b to the n, right? Right. And so we don't have this rule for any numbers other than like 1, 2, 3, 4, 5. X to the 1, x to the 2, x to the 0, etc. But in fact, it's true. In fact, it is true for all real numbers. So basically, for any power that's a real number, in fact, it's true that the derivative of x to the p is px to the p minus 1. Okay. So the power rule holds for all numbers. Okay. So for example, if I said I'd like you to take the derivative f of x is, say, the square root of x to the 5th minus 3x to the minus 7. Then you can just apply the power rule to both of these things. Okay, so it works for these things. Okay, maybe take 10 seconds and write down what this would be, just by applying the power rule. Okay. Is there anybody who is new to this and would like to venture their answer? I think it's better if somebody who hasn't seen this sort of stuff before, tries it. How about you, Gwyneth? You're looking at me. Too bad.
No, I have a blank page.
You have a blank page. Okay, that's good. Thank you. So, so here you've got the square root of x to the 5th, right? Right. So that's x to the 5th square root, right? X to the 5th square root. Here you have. So this one, it's just a matter of disguise, basically, right? You have this square root of x to the 5th. You'd like to have something like x to the p, right? But it's not quite in that form. It's just a small disguise. You see that it's actually the square root of x to the 5th. In other words, it's x to the 5 halves, right? So once you peel off that disguise, then it's something that you see that you can apply the power rule to. So when you differentiate it, well, you're going to differentiate each part. So the derivative of this is going to be what?
5 halves x to the 4 halves?
The 3 halves, actually, right? Because you're going to subtract off 1. 5 halves minus 2 halves. Right? 5 halves minus 1, in other words, 5 halves.
Oh, I see. Yeah.
3 halves. So you get 5 halves x to the 3 halves.
Okay.
Right? And then the second one, you've got this minus 3 times, you're taking the derivative of minus 3x to the minus 7. That's the same thing as minus 3 times the derivative of x to the minus 7 using our properties of derivative. Right? So what's the derivative of x to the minus 7? It'll be
7x to the 6th.
actually, so you have a minus 7 here. So you bring down the minus 7. X to the minus 7 minus 1, so it'll be negative 8.
Oh, God, Lord.
It's okay. It's okay, don't worry. Don't worry. Okay. So you just do it like this. Okay. So, right, so it's just a matter of applying the rule. The rule says bring down the power, and reduce the exponent by 1. Right? So bring down the power, subtract 1 from the exponent, bring down the power, subtract 1 from that exponent. Okay, yeah, Mariah.
Rational numbers are still real, right?
Yeah. So this is also true for if we had x to the pi, right? What's the derivative of x to the pi? Pi x to the pi minus 1, right? Still gonna be true. Okay, so true for irrational powers as well. Okay. So remember how we defined irrational powers? That was pretty bad, right? Do you remember how we defined irrational powers? How do we define irrational powers? Does anyone remember? Yeah, Mariah.
If you have like 2 to the pi, it would be 2 to the 3 times 2 to the point of 1 times 2 to the point of 3.
Yeah, you have to set up a sequence and then find the limit of this increasing sequence, right? So it's actually pretty complicated. And so you think, if we want to talk about why this is true, do we have to go through those limits? Maybe, but there's another way around it. We're not going to explain this right now, but in the next section we'll get to it. Okay. So right now let's put it on hold before we get something handy. Okay. In any case, the power rule holds for all numbers. Now you can use it as you've been wanting to all this time. Okay. I know some people have been saying, but isn't the power rule true for all numbers? Yes, it is. The proof of that will actually rely on the next fact, which is the derivative. The derivative of the exponential function. Okay, so we will actually need this to get the power rule. Okay, and notice that people often write x of x instead of e to the x. These are the same thing. E to the x and x of x, same thing. Okay. Sometimes it's handier to write it like this. Okay. Who knows what the derivative of e to the x is? Who knows what the derivative is? It turns out to be it's e to the x again. E to the x, the derivative of e to the x. So you think about what e to the x looks like, right? E to the x is this function. What does it look like? Well, at 0, it's e to the 0, right? So what's e to the 0? 1. So that's 1. At 1, it's e to the 1, right? So that's somewhere before 3. It's not here, right? At 2, it's e squared, right? Somewhere around 9, right? At negative 1, it's 1 over e, right? 1 over e, so somewhere around here. Right? So you have this function. That's what e to the x looks like, right? And it turns out that the derivative of e to the x is e to the x again. Okay, so if I take a point, C, and I look at what does this tell me graphically? If I take this point C, the derivative, right? The derivative of e to the x, right? If f of x is e to the x, f prime x is also e to the x. Right? So what does that tell me about the graph here? What does that tell me about the graph? Can anyone make some statement about this? Yes, Stefano.
That the instantaneous slope
Yeah.
increase there is the same as the value that's there.
Yeah, yeah, exactly, right? So, right, this height here is e to the c, and the slope here, the slope of the tangent line, right, slope of the tangent line is also e to the c, right? And that's true at every single point, right? At every c you take, the height is e to the c, and the slope of the tangent line is e to the c. Okay. So, for example, if I look at the tangent line, here's the question for you. If I look at the tangent line, where does it intersect the x-axis? Where does it intersect the x-axis? I'll let you think about it for 1 minute, okay? Or just 30 seconds. Okay, turn to somebody next to you and talk about it. Say, I think it intersects the x-axis here because of such and such and such and such. Being able to talk about that is useful.
Because like I'm thinking of like x0, which is like look at intersects with the origin, so maybe it's maybe one line. Or just
Okay. Yeah, so I should say, I just want to make a comment that being able to talk about mathematics is really a useful skill, and it will improve your ability to learn mathematics. When I was in college, I always worked by myself. I went to the library and just worked by myself. And but I had friends who always talked with each other and worked on things together. And I think they developed this sort of social mathematics that I never did. And that I think that was really something that I lack. And it was really good for people.
So I don't think you like it at all. You're insecure.
Yeah, I am now. But it's not quite the same thing, actually. To talk about something you don't know and talk about something that you do know, right? Like an sort of exploratory talking and rather like expository talking. It's different. I don't know how to do that. Okay. So can somebody tell me about this? What do you think happens? Claire, you had it first.
Yeah. Does it intersect the origin?
Does it intersect the origin? Why do you say that?
Just because I'm thinking about the line y equals x.
Yeah.
And how like all the x coordinates are the same as the y coordinates.
Yes.
So I don't know. Maybe that somehow relates.
Okay. Let's think like this. Here you have your function is at a height e to the c, and the slope is e to the c. What is the slope? What does that mean about the slope? Right. That how far does your line move with each unit? Like if I step over one step, then how much higher does my line get? E to the c. What?
E to the c.
E to the c. Right. Right. The slope. That's what the slope means. If you move over 1, then the line moves up m, right? So what does that mean? If I step back 1, then where am I going to be?
0.
At 0, right? I'll be at 0. So where does it intersect? It will intersect at c minus 1. Right, the slope is e to the c. My height is e to the c. So if I move back 1, I'm going to drop down e to the c. I'll be at 0. Right? So does people see that? Gwen?
It feels arbitrary. Like does that work for any c?
Does it work for any c? Well, yeah, that's right. That's right. It is arbitrary. It will work for any c. Yeah, for at every point, if I take the tangent line, if I took the tangent line over here, this is my c. Well then, same thing. My height will be e to the c. And my height and the slope of my tangent line will be e to the c. But now that's a higher slope now. That's a bigger slope. and it will drop me down. It will drop me down in one unit of time. It will drop me down all the way down to the
Oh, okay.
to 0. Yeah, correct.
Why is C 1? Like, why is C minus 1 0? I don't understand that.
Okay, so at time c, the height is e to the c, right? The slope of the tangent line is e to the c, right? So the slope of this line, m is e to the c. So m being e to the c means that you know the slope that your line looks like. If you do a right triangle line, it would be like this, right? Right. So I'm going to draw that right triangle here. This is e to the c, and this is 1. Right. So what does the slope tell you? It tells you how far you move in 1 unit of time. Right. If you move 1 unit down here, how much does the tangent line drop? Right. So so the tangent line is moving e to the c units every 1 unit of time. So if we move back 1 unit of time, it will have dropped back. It will have dropped down e to the c units. But it was at height e to the c to begin with, so it'll go down to 0.
Oh, okay.
Right. It was at height e to the c, e to the c. In 1 second, it moves e to the c.
Okay.
So it comes down to 0. And that's true of every point. So what is this saying? Just to give you some geometric sense of what this is, what does it say? It says that if you take the tangent line at any point, it's always going to be 1 unit over. It's always going to intersect 1 unit over. So, right. If I take the tangent line here, if I took the point 2, and I took the tangent line, it would intersect at 1. Right? If I took the tangent line at this point, it's going to intersect one unit over, etc. Okay. And in fact, it's basically the only function that does this. In fact, it is the only property. It is the only function that has this property. Okay. Why is this true? Again, why is this true? Let's think about it. D dx, e to the x, that's the limit as h goes to 0 of e to the x plus h minus e to the x over h. Right? So we're hoping that that's going to be e to the x. We're hoping that it's going to be e to the x. What should we do? What should we do? Well, let's factor out an e to the x. Right? This is e to the x, e to the h minus 1 over h as h goes to 0. Okay. Is everyone okay with that?
Yeah.
Okay. So this e to the x doesn't depend on h, so I'm just going to pull it out. Okay. I'm going to pull it out. It's constant with respect to h. As h changes, this e to the x doesn't depend on h at all, so I can pull it out, and you get e to the x times this number.
Let's see.
What?
I'm not just using.
And this number, what? This number turns out to be 1. Okay. We actually can't show this at this point, so we don't know. This is some number. Okay. It's some number. So at this point, what we know is that the derivative of e to the x turns out to be something times e to the x. Okay. But in fact, that number we'll see later turns out to be 1. So we'll see that later.
It looks like it'd be 0.
It looks like it's going to be 0. Yeah, what do people think about it? I've already told you it's going to be 1, but it looks like you get e to the h is going to 0, right? And so this e to the h looks like it's going to head towards 1, right? Going to head towards 1. You get 1 minus 1 over something that's also going to 0, right? So you get basically some sort of 0 over 0. And then at that point, it's not really clear what's going to happen, right? If I said, what's the limit of x squared over x as x goes to 0? What's that?
0.
0, right? That's going to be 0 because it's basically the same thing as this, right? You can cancel out an x from top and bottom. You get limit of x as x goes to 0. That's 0. Right. What's the limit of x over x cubed, say, as x goes to 0? It's better than undefined. It's better than there is no limit. Infinity, right? It's infinite. It's a positive infinity, right? Because this is the limit of 1 over x squared as x goes to 0, right? The limit of 1 over x squared as x goes to 0, right? Which is infinite. This is positive infinity. So the point I'm making is that when you get 0 over 0, it's not really clear what happens, right? You could get a whole range of answers, right? You might have like this. What's the limit of this as x goes to 0? 1, right? Right? It sort of depends on who wins the race, who's going faster. If they're going at an equal speed, you're going to get a constant, right? Here, this guy's going faster, the x squared is going faster, so it's going to win and become 0. The x cubed is going faster than the x, so you get infinity.
If you had an x to the h minus 1 over h, would
Yeah.
that be 0, or would that also be 1?
It's going to turn out to be 1.
Okay. So it doesn't matter that it's e, it's just any.
It's no. It does matter.
Oh.
It does matter. But what we'll see later, and this is what's called L'Hopital's rule for those of you who've seen it before. L'Hopital's rule tells you who wins the race, basically. Okay. And in this case, it's a tie, right? Both of these guys go to 0 equally fast, and so you balance out just like this, and you get 1.
Right now, which one wins when there's a square root involved?
I'm sorry?
Like, I remember they quitted in the previous, and then the test, the practice test.
Yes.
There were problems where like a limit approaches infinity, and it was either the denominator or the numerator had a square root, and I didn't know how to do it.
Yeah, we can talk about that maybe after classes.
Okay, thank you.
Okay. Okay, so for practice, just as an exercise to make sure you understand this, I'd like you to differentiate this one, e to the x plus 1 over e to the x minus 1. Okay. So just differentiate it. It's not exciting, just do it. Sarah, do you want to say? What do you do?
I got 1.
Hmm?
I got 1.
1?
Yeah.
How did you get 1?
Because e to the x is, the derivative of e to the x is e to the x. And then, like, you exclude 1 because it doesn't have to do with x. So then e to the x over e to the x is 1.
So we're asking for the derivative, right? We want to differentiate this thing. This is so this is a quotient. This is what you see here is that it's a quotient of functions,
Okay.
right? So you want to use the quotient rule. Right? You've got one function over another function, and you're asked to differentiate it.
Okay.
So what you do is you take you just remember, you take the bottom times the derivative of the top, you get the bottom function times the derivative of the top function. Well, what's the derivative of the top function?
Just e to the x.
Yes,
Yeah, you
just e to the x, minus the top times the derivative of the bottom. What's the derivative of the bottom?
E to the x.
E to the x again. Yeah. Over the bottom square.
You missed the
Wait,
X, yeah,
x
plus
plus
one.
1.
Oh, thank you. Bottom times the top minus the top times the derivative of the bottom over the bottom square. And you can simplify it further if you like, but that's it. Yes, Kimai?
That's my question. I was like in the homework or in problems, do we have to simplify?
Yes, please, for the sake of the graders, because otherwise you might have some large expression and say this is the answer, and the grader would then have to do that work herself, which is trouble.
Wait. So
Do simplify your answers for the homework. I don't care right here, but on homework it's useful. Yes.
Would you mind doing it now? Just
Sure. Okay. So what do you get? You have e to the x minus 1 times e to the x. So each of these guys gets multiplied by e to the x. Right? So you get e to the 2x minus e to the x. Right? And then here you've got minus e to the x times these things. So e to the 2x plus e to the x. Everything over e to the x minus 1 quantity squared. Right? So you get e to the 2x minus e to the x minus e to the 2x minus e to the x. Everything over e to the x minus 1 quantity squared. This minus this, you get minus 2 e to the x over the e to the x minus 1 quantity squared.
So did we get that wrong if we didn't simplify on the homework?
That's up to the graders, but if I were the grader, I would say you have to simplify it,
I see, yeah, okay.
because otherwise I have to do all your you might have gotten some completely different expression or
Yeah.
something and said this is the answer. Then I have to work through it and see if it is a bad answer or not. They don't have that kind of time. Yeah. Now on an exam, I think you don't have to worry so much, because for me I'll just say, oh, did she apply the property correctly? Yes, the end. Right? I don't really, the rest to me on an exam doesn't really matter. All I'm looking for is not whether or not, I'm not looking to see if you can do elementary arithmetic. I'm looking to see if you know the property. Right? So. Okay. So, not much exciting has happened today. We've introduced the power rule, but we haven't explained it. We've introduced the derivative of the exponential function. That's actually really important, but that's just one thing. The next section is about differentiating compositions of functions. So remember what that's about, right? Right, you have two functions in succession, right? You have one function followed by another function, right? G composed with f, right? G composed of f of x is G of f of x. Right? Recall the composition of functions, right? G composed with f means you first take f of x, you take f, put x into it, and then take f of x and put that into G. Okay? Okay, so here's the motivation. Let f of x be x plus 3x to the 100th power. Okay, and I would like to know f prime x. I'd like to know f prime x. What's f prime x? At this point, how can we do it? We don't have any good way to do it. We have only the product rule, right? We have only the product rule. So what we'd have to do is multiply this thing out, right? You could write this out. One thing you could do is just multiply the whole thing out and then differentiate it, right? You could make a gigantic Pascal's triangle, say, right? And then use that gigantic Pascal's triangle, get the 100th row of the Pascal's triangle, figure out your coefficients, blah, blah, blah. Okay, that's one way you could do it. Right? Another way would be, this is even worse, right? Don't use Pascal's triangle, but use the product rule, right? And say, I'm going to take the first guy times the derivative of the second guy. Right? To get that, I need to get the first guy times the derivative of that second guy, back and forth, right? Times the second guy times the derivative of the first guy, you know, et cetera, et cetera. Right? You could use the product rule, and those are the two ways you could do it. Right? Victor, what were you going to say?
I was going to say let g of x equal x.
Don't say it. Are you going to use the chain rule? You're going to use the chain rule. No.
I was going to use a composition.
Yes, don't do it. Okay. So, yeah. So, fortunately, there's a better way, which is called the chain rule, which tells you about how to differentiate compositions, right? Because what this is actually, you recognize this as a composition of functions. Right? There's first this x cubed plus x function, and it's put, the output of that is put into the x to the 100 function. Right? There are two functions. You can recognize this as a composition of functions. Right? Right. So here's the chain rule. What it says is that if f is differentiable at c and g is differentiable at f of c, then the composition g of f is differentiable at c with its derivative being the product of the derivative of g at f of c and the derivative of f at c. So here's your point C. C gets mapped to f of c. F of c gets mapped to g of f of c. Okay. And what the chain rule tells you is that the derivative of the composition at c is going to be the product of the derivatives. Can you see, Asha? G of f, the derivative of g of f being the product of the derivatives at the right places. Okay, right? The derivative of a composition is the product of the derivatives, but they have to be evaluated at the right places, right? F was differentiable at c. You take the derivative of f at c. You take the derivative of g at f of c. Right? F was differentiable at c, g was differentiable at f of c. So it has to be at the right places. It's not true that it's not like g prime of c, f prime of c. That's not. It's g prime of f of c, f prime of c. Okay. So so for example, if we look at this function, x cubed plus x to the 100, and let me write it as h, so I can use f and g here. Okay. Then what this is it's a composition of two functions, right? Where the first function is is x cubed plus x, right? And the second function is what?
X to the 100.
X to the 100. Okay. So, right. So what's going to be the derivative, right? H prime of x is going to be g prime evaluated at f of x times f prime evaluated at x. Okay. So what is that? That's g prime, right? What's g prime? What's g prime? Somebody just read it off for me.
100x to the 99.
100 x to the 99. And what's f prime? 3x squared plus 1.
Oh,
Okay. Okay. Right. So you get g prime evaluated at f of x. Right. G prime evaluated at f of x. So that's going to be 100 x cubed plus x to the 99. And you get f prime of x times 3x squared plus 1. Yeah, Mariah.
If it keeps going, like if you g of h of f of k,
Yeah.
is that like, does the pattern just repeat?
Yeah, you just basically use the chain rule over and over.
Okay.
Just iteratively use the chain rule. So we'll do an example in a second. Okay. Is everyone okay? Is everyone okay with this? Particularly people who haven't seen it before, right? The derivative of a composition. So you have this function. Half of the game is recognizing this as a composition, right? So you say, oh, okay, I can express this as one function going into another function. Okay, that's half of the game. Yeah, Sarah.
Wait, so, oh wait, no, never mind. I get it. Sorry.
Great.
It was answer my own question.
So half of the game is recognizing this as a composition. And once you recognize it as a composition, then you just apply the rule, right? So you say, I've got this outside function x to 100. I differentiate it, right? I'm going to get 100 blah to the 99. I evaluate it at the inside function. The derivative of the outside function evaluated at the inside function times the derivative of the inside function. Yes?
Are you using the product rule to make that?
Nope.
Okay, it's just a different rule.
Yeah, this is a completely different rule.
Okay.
Yeah.
Good.
Yeah. So no, it's not the product rule. It's the composition rule. Yeah, you see you see that it's sort of what you hoped for the product rule, right? That maybe you hoped for the product rule that the derivative of a product would be some sort of product of derivatives. In fact, it's the derivative of a composition that turns out to be the product of the derivatives. Yeah, but evaluated at the right places. Okay, so let me ask you to try one. Here's another. Sin x plus x squared to the 6. Okay, so take 30 seconds and write down an answer. What's the derivative of that?
It's sin x plus x.
Sin x plus x squared quantity to the 6. Yeah, that's a plus. who would like to make a guess? If you, preferably somebody who feels a bit uncertain about it. Anybody willing to be bold? Anybody? Go ahead. You missed it. Yep.
Surely you guessed.
Go ahead. Yeah.
I got 6 paren sin x plus x squared to the 5th times cosine x plus 2x.
Very good. That's exactly right.
Really?
Yes. Yes. Great. Exactly. Right.
Yes.
Right. So you've got your inside function, right? Your inside function. You've got your outside function. Right. You differentiate the outside function. You differentiate the outside function and evaluate it at the inside function. Right? You differentiate the outside function, 6x to the 5th, evaluate it at the inside function, times the derivative of the inside function. Very good. Okay, let me do a triple. Suppose we have something like this. 1, 2, 3. 1, 2, 3. It's no more complicated than the previous, right? Right. You take, right. Here's your outside function, say. So let's take this as our inside function. Right. You take the derivative of your. So just watch. Everybody, just watch. You take the derivative of your outside function. What's that? Cosine. Evaluate it at your inside function. Right? Times the derivative of your inside function. Oh, this inside function is also composition. So I do it again. Right? So I want the derivative of the inside function. Right? But this is also composition, so I just do it again. Take the derivative of the outside function, what's that? Negative sine x. Negative sine, evaluate it at the inside function, times the derivative of the inside function. What's that? Right? So you just iteratively apply the chain rule, right? And if you had 4, you would just do it. You would just apply the chain rule, 3 times rather than 2 times. Okay. So it's just done, right? You see what we needed to do: evaluate the outside guy's derivative here, and then differentiate the inside guy. That guy was a composition. Just use the chain rule again. Okay, so it's simple.
You multiply it by that, and would you get the product of the chain rule again, or just the chain rule? That makes sense. Because you found the first one, and then you used to get the second one, the chain rule as well. So do you multiply the first one by the chain rule and then the derivative, or the first one just by what you get when you take the derivative of that chain rule?
Just multiply this thing by what you get from the chain rule.
Okay.
Apply to this.
Okay.
Let me quickly just make one comment about notation. So this is the Newtonian notation. Some people, you could write this as, again, there are sort of multiple ways of writing it. You could write it like this. Right? The derivative of the composition evaluated at x equals c. Some people write it like this. The derivative of g with respect to its variable, right? The derivative of g with respect to its variable evaluated when its variable is f of c times the derivative of f with respect to x when x is c. It's the same thing. Right? G f of c times c. Right? the derivative evaluated at f of c, this guy's derivative evaluated at c. Right? Often people write the following: dg dx equals dg df df dx. Often you'll see the chain rule expressed as if it were some sort of rule about fractions, right? That you can somehow cancel off the f's and then get dx, the derivative of the composition with respect to x. Okay, but this is very misleading, and this sort of reasoning doesn't work in higher dimensions. So I think it's best just to don't. The warning is don't think that there's some sort of fraction thing going on here. It's not a fraction thing. Okay. So I'm sorry. That's it for today. Sorry to keep you waiting.